Hey. Okay. Oh, different space.
Yeah, I'm in my
What?
living room.
What?
I'm in my living room.
Ah, gotcha. Okay. And let's see. So hopefully everything's today. Um. Oh, need the other person's online too. So let's even get her on. Mm, You're not sick, are you?
I'm always sick with my kid.
Yeah, I've just been through that. So.
It's not bad. It's runniness,
Yeah, just stuff to be annoying.
as always.
Yeah.
So tomorrow, are you free for
Yeah.
around 5 or 5:30?
Yeah. Totally.
I'll get there as soon as I can. My issue with the homework is just the notation. That's just what's killing me.
Oh yeah.
Um,
Well.
if I could see examples of certain things, then
mm,
I could for sure do it.
Oh yeah.
It's that's what I'm having difficulty with.
Oh, everybody has trouble with the homework. So I,
Well,
I think most people haven't touched it yet, but trust me, it's universal. So or it will be.
I figured it out, and I know what like rank A is and all that. I just
Yeah.
lots of questions.
Okay. I'll be ready.
Hi.
Hey. No.
Oh my gosh, the video is so much better.
Oh, good. Okay, that was easy. Yeah, yeah, because after you disconnected and recording off a webcam, the file was so huge that it
Oh,
took forever to upload. But yeah, now it should be a
I'm
lot
pretty
easier.
sure it was my internet connection that was causing a problem.
Okay,
So,
yeah.
yeah.
So, but was that at school? Or
Yeah.
oh, hmm.
Now I'm at home, so my home internet is so much faster.
That's sad that campus doesn't provide as good a connection as home. Um, yeah, I'm gonna start on page 38. Yeah.
Okay.
Um, okay. So I was still waiting for everybody else to get here. Um, okay. Okay. Um, Down to coast, can you zoom your camera out?
We have no control over zooming the camera out.
Even your own camera?
Yeah, we can't even adjust it down here. This is a non-traditional IBM room. It's actually in the geography lab, so it doesn't work like the others.
Now, was this the same room you were in last week?
Yes, it is.
Okay.
There's no students here yet. It's just a facilitator.
Okay. Gotcha. Um, um, yeah, 'cause I tried zooming it out too, and I couldn't.
Yeah, it's a whole different program. It's set up with this particular machine, so it doesn't allow us to do much of anything.
Oh, okay. That's really inconvenient.
I understand.
Okay. Yeah, that's what we'll be thinking about that. I can't. And they can't control hers either, so that's our view. Well, once they can see us, and oh, there you. You're it. Okay. Let's see. 1, 2, 3, 4, 5, 6. Okay.
Okay. Area right here, that's all we can see. Over here. Oh, there's some road, there's nothing. I should back row.
Is that Yulia?
Yes.
Okay. I can see your head.
Can't control the camera. I can't get from that space.
The only one here so far.
Okay, good to know. Yeah, so I probably won't be able to see them, so let me know when they show. If anybody does. Okay. Oh, so now you learn something extra about eigenvalues. So now you learn something extra about eigenvalues and eigenvectors. Well, not yet, but by the end of the semester.
That's what I'm saying. Not yet. It's been the story of his class.
Sorry, I can't walk and carry things.
Okay, good to know.
It's like the butter bringing an apple to. That's a girl. It's like girl.
I'll take it. Are you gonna wait on like
No, for a little while, but
how's on now?
in a couple minutes. Why?
It's like
Oh yeah, go ahead.
Ask me figure whatever it was. Figure like an hour to figure out like a dream. You know what I'm talking about?
She was asking permission to, he was saying that she was wasting time,
Who was?
asking permission.
Last week.
Go to
I was
it.
Oh right, yeah.
She like wastes more time asking if she can do something than other take to just go do.
Oh,
Let me find it's not doing this time.
okay. Yeah, I kind of figured.
But so after we find X, Y, Z, and W, we know which yours are. And so we're trying to find L inverse and U inverse, but it's L tilde where it's got that incomplete bar factorization. So
Yeah.
they need to find L inverse and U inverse.
Right.
So that's what I did here.
Oh,
And
It's
I
not
just
gonna work
I
like
was
that.
calling it. Okay.
oh, I see what you're doing.
Yeah, I
Never
was
mind.
just
Okay, so
calling
that's
it
okay. Yeah.
to solve for these guys.
Yeah.
So I multiplied it out, and then that's I,
Yeah.
and then that's
Yeah.
0.
Okay.
And so I must have been something wrong in here,
Oh,
because when I multiplied it out, I found L inverse and U inverse, and I multiplied it out.
and it checked off. Okay.
No, it did not.
Oh.
So, like, I was in the process of multiplying it out, and it didn't look like it was going to work
Oh,
out.
but I mean, did you check like multiplying this by L?
No.
Okay, check that first.
Okay. And then we'll know where the problem is.
Yeah.
Okay. All right.
Yeah. All right. If there is a mistake, the most common thing would probably like something on the wrong side or whatever, like wrong direction multiply.
Okay.
So.
Yeah.
Okay. Oh, no one else here, Leah?
No.
Okay.
I just see me today.
Alrighty. Yeah, 'cause no one told me that they were going to miss down there. And I don't know if they went to the other room by mistake.
Well, there's a big sign on it at that point. That's great.
Okay.
And it's like 3 doors down, so it's
Oh, okay. So, all right, it's not that then. Okay. Well, because it's 4 past. All right. You get 1 more minute.
I looked at the MATLAB tutorial
Oh, yeah. Well, at least you got something out of it then. Something entertaining. Actually, I was surprised you look at it because I know you know MATLAB. So.
I do, and I wasn't gonna look at it, but then you asked, I was like, well, maybe he knows something that I don't know. You know, it's always good to look at.
Oh, no, I figured you in particular were good to go. Okay. All right. Well, that's enough waiting. Okay. Do you need me zoomed in down there, or?
No, I'm good. I'm good. If you could just pan left and right, I can see you just fine.
Okay. Yep. Yeah, and this time we should have one full high quality video coming up afterwards. So, has anyone viewed the video from last time on YouTube?
I watched the second half of it, and it seemed I could see everything.
Okay.
There was a glare on that board, but it was only like in the top right.
Yeah. Yeah, the glare is kind of unfortunate because we can't really do anything about it. But actually, the trouble is from my point here. Yeah, I can kind of see it, but yeah, I don't know what.
It was only. I mean, there was a very small part of the equation, but
I guess toward the top or something. Is where...
it was the very top, like
Yeah.
maybe a foot from the center point.
Okay, gotcha.
So it wasn't too bad. It was maybe a very small part of the equation.
Okay, good to know.
If you watched it long enough, it would kind of clear up. It was weird. So you can
Oh.
make it out.
Yeah. All right. Okay, so. So, eigenvalues and eigenvectors, and it's not until the end of the semester where we actually get into techniques for computing them, but certainly some familiarity for basic properties is needed at various other points in the semester, so that's why I'm introducing them now. Where I left off last time is if I have a sequence of vectors defined this way, where each new vector is the previous vector multiplied by some given matrix A, and the first vector in the sequence is just something arbitrarily chosen. What I gave as a sufficient condition is if the norm of A is less than 1, and this could be any matrix norm, 1 norm, 2 norm, infinity norm, Frobenius norm. If any norm of A is 1, then the sequence of vectors converges to 0 as k goes to infinity. Now, so this is an if, it is not an if and only if. So this condition here is it is sufficient, but it's not necessary. So if a norm of A is greater than or equal to 1, it's possible that the sequence could still go to 0. So what we want is that this sequence converges to a 0 vector if and only if what? What condition does A need to satisfy? Something that is necessary and sufficient. And that's where we get into, in order to state such a condition, we actually need eigenvalues. So go ahead and give some, okay, well, you may be familiar with them from some other class, but I'll re-give a definition, some important properties, and then we'll get to this condition. Okay. Well, be careful with all my drinks here. Okay. All right. if you have this relationship, a times x is equal to lambda times x, where x has to be a non-zero vector, and lambda is a number, could be real or complex. So this relationship is satisfied for some x and some lambda. We say that x is an eigenvector of A, and lambda is the corresponding eigenvalue of A. And I say corresponding, meaning that eigenvalues and eigenvectors occur in pairs. All right. Now, why eigenvalues and eigenvectors are important is here we have on the left side, we have matrix vector multiplication. I've given you a formula for that. It's rather tedious to apply. You're having to carry a summation just to get each entry of the product. On the other hand, on the right side, we have scalar multiplication of a vector, a very simple operation. You're just taking each component of x and multiplying it by lambda. So eigenvectors are the specific vectors for corresponding to this matrix A, such that this complicated operation reduces to this extremely simple operation. And that's nice because it gives us a better understanding of how A acts on any vector. So it gives us insight into the behavior of A as a linear transformation on the entire vector space. For instance, what if all of the eigenvalues are less than 1 in magnitude? So basically, A shrinks any vector. Or what if you have some eigenvalues positives, some negatives? So some vectors A will reflect across a certain hyperplane, or others it'll keep in the same hyperplane, and so on. So at least instead of trying to understand A by looking at its entries, which generally doesn't give us any insight at all, unless A is a very simple matrix of a nice simple structure, these eigenvalues can tell us more. Now, one way to characterize these eigenvalues, and this is actually how you computed them in a first linear algebra course, is by rearranging this equation. So if I just take this and rearrange it, I have, I'll move lambda x over to the other side, and I will factor out an x. So I have a minus lambda I times x is equal to 0. Now, keeping in mind that x is a non-zero vector, we have a situation where we have a matrix times a non-zero vector gives us a 0 vector. The only way that can happen is if the matrix involved, a minus lambda I, is a singular matrix. In other words, a matrix that is not invertible. So I gave several conditions about a singular matrix that are all equivalent to one another. One of those conditions is that if a matrix is singular, its determinant must be 0. Okay. So now A and the eigenvalue lambda satisfy this condition. Now, if you were to take a given matrix A and A minus lambda times I identity and then take its determinant, what you would find is this expression, this determinant, is actually a polynomial in lambda, and it has degree n, where A is an n by n matrix. So this determinant we call the characteristic polynomial of A, and it has degree n. And since the eigenvalues are those values for which this polynomial is equal to 0, that means that the eigenvalues are the roots of this characteristic polynomial. So that's one way to find them. So what happens if you may recall from your first linear algebra course, learning about eigenvalues, for your exercise, you're probably given a small matrix, maybe a 3x3, and asked to compute the eigenvalues by forming a characteristic polynomial, since you knew how to compute determinants, and computing its roots by whatever means, from factoring or whatever. And then, once you had those eigenvalues, then you could go back and solve this system to get the eigenvectors. So, since the eigenvalues are polynomial roots, how many eigenvalues could we possibly have? N, because a polynomial of degree n has n roots. Now, keep in mind though, roots may repeat, so you're not necessarily going to get n distinct eigenvalues, but you're going to have at most n. Also, even if a matrix A is real, so the characteristic polynomial has real coefficients, the eigenvalues can still be complex. But what happens in that case? What? Yeah, they occur in complex conjugate pairs. So you have that limitation at least. So what's going to happen? So here's the thing that's rather backwards about all this. In your first linear algebra course, you are taught to compute eigenvalues by computing polynomial roots by whatever means you learned before. But in MATLAB, it goes backwards. If you use MATLAB's function to compute polynomial roots, so that's your objective is polynomial roots, it will form a matrix whose characteristic polynomial is the polynomial you're trying to get the roots of, and then compute its eigenvalues by other means. Those other means is we'll cover at the end of the semester. And that turns out to be a whole lot more practical than root finding methods that you learn in your algebra class when you're getting to polynomials of larger degree. And when we deal with eigenvalues that may be matrices that may have complex eigenvalues, we're still going to perform exclusively real computations, but we'll get to a point where we can keep everything real and get down to the very end, and then we can, at the very last step, get those complex conjugate pairs of eigenvalues. Okay. And what we'll find also is that repeated eigenvalues, because polynomials can have repeated roots, so we can have repeated eigenvalues, actually can cause difficulty for the numerical methods that we're going to learn. So repeated eigenvalues are bad. Okay, so now some properties of eigenvalues that are going to be useful to us. Oh, some more people have shown up down there? Okay. I see Kilia. Anybody else?
No, just those two.
Okay. All right. Okay. So, first, each eigenvalue that you find has at least one linearly independent eigenvector. Now, the linearly independent is important because if you think of the equation a times x equals lambda times x, you can take an equation and multiply it by any scalar. So any multiple, any non-zero multiple of an eigenvector is also an eigenvector. Those are not worth talking about. So generally, when you find an eigenvalue, most of the time, you're only going to have one eigenvector that goes with it, but and you're going to have at least one. Sometimes, when an eigenvalue repeats, you might have more than one linearly independent eigenvector. But repeated eigenvalues, again, they're problematic. You can have an eigenvalue occur like 5 times as a root of a characteristic polynomial. And in that case, it can have anywhere from 1 to 5 linearly independent eigenvalues. It just depends on the structure of a matrix. Second, if you have a relationship between matrices A and B like this, B is equal to P times A times P inverse, for some P that has to be invertible since I'm using the inverse, then the matrices A and B are said to be similar. And this expression, where we take A and multiply on the left by P and multiply on the right by P inverse, that is called a similarity transformation. Okay. When we get to computing eigenvalues and eigenvectors, similarity transformation is the main tool that we're going to use. Because the idea is, starting from our given matrix A, we can perform similarity transformations on A to get to some matrix B whose eigenvalues are much easier to compute. Basically, an eigenvalue revealing form. This is kind of like when you're solving system linear equations using row operations. Why do you perform the row operations? To reduce the matrix to like row echelon form, some form where the system becomes easier to solve. This is the same principle, it's just harder to pull off. Okay, because what happens is, so I should give the definition of similar. Two matrices that are similar have the same eigenvalues. So because this transformation preserves eigenvalues, that's why it's useful to actually obtain them, because hopefully B is in some eigenvalue revealing form. Okay. If A is a symmetric matrix, A equals A transpose, and this is a case where A is real, or in a complex case, if A is equal to its Hermitian transpose, so it's transpose complex conjugate, then the eigenvalues are real. So when we get to studying eigenvalue computation, we'll look at the case of a general matrix and also a symmetric or Hermitian matrix, because in that case, because we know the eigenvalues are real, the whole problem simplifies considerably. Okay. Similarly, if it's skew symmetric or skew Hermitian, A has purely imaginary eigenvalues, or 0 is allowed. In other words, all the eigenvalues have to have a 0 real part. Just as in this case, they have to have a 0 imaginary part. Okay, actually, yep, still more properties. Okay, actually, this next property, it's on my list, came up in earlier, but if A is real and U plus IV, so this complex number is an eigenvalue, then its complex conjugate, lambda bar, U minus IV, is also an eigenvalue. Just in other words, the eigenvalues occur for real matrix in complex conjugate pairs. Okay. Now,
Dr. Lambert.
yes.
I'm sorry. Can you zoom in a little bit? Sorry.
Oh, sorry, I accidentally used a smaller font there. Okay.
How is that? Can you zoom in more?
That's good.
Okay.
Thank you.
I'll try to use a larger font from this point. Okay. It's too bad I can't just do like a drop down in Word and just make my text bigger. But okay. This property is particularly useful for computing eigenvalues. That is, if A is a triangular matrix, it doesn't matter whether it's upper or lower. So whether it has this structure for a lower triangular matrix or this structure for an upper triangular matrix, then the eigenvalues are equal to the diagonal entries. And this comes from the fact that the determinant of such a matrix is just equal to the product of the diagonal entries. So the idea is behind eigenvalue computing algorithms is to perform similarity transformations on A to reduce A to triangular form, and then you can just read the eigenvalues off the diagonal. Okay. Okay, a couple more. The determinant of A is equal to the product of all of the eigenvalues of A. And then the trace of A, which is abbreviated as TR of A, the way it's defined is it's a sum of all of the diagonal entries, but that is equal to the sum of all the eigenvalues. So the idea is if you perform some similarity transformation to make A to a triangular matrix and then sum its diagonal entries, that similarity transformation does not affect this sum. So the trace is something that's really easy to compute, and so now at least you know the sum of all the eigenvalues. This is really nice for something simple like a 2 by 2 matrix, because it's easy to compute a trace, it's easy to compute a determinant, and from there you can backtrack from that to the eigenvalues, because if you know the product of two numbers and their sum, you can solve for the numbers. Okay. All right. So now that I have these properties, which we'll be using from time to time throughout the semester, I could finally get to the reason why I introduced eigenvalues at this point in the first place, and it's talking about sequences of vectors converging to the zero vector. But in order to state this condition, I need to introduce some notation that's going to be often used anyway. Now, typically, The eigenvalues of a matrix, then to help with the discussion, are they're often ordered, and since they can be real or complex, we order them according to their complex modulus, so their absolute value. So lambda 1 of A is that be the largest. Okay. So lambda 1 is used to refer to the largest in magnitude down to lambda n. And so I use this notation to refer to the eigenvalues of a specific matrix. If it's clear from the context what matrix I'm referring to, then chances are I would leave this off. But in case there's any ambiguity, then we'll include this. Okay. So one helpful definition, the spectral radius. Actually, before I do that, the spectrum of A, that's the set of eigenvalues of A. Okay. And to go with that, the spectral radius of A is denoted by rho of A, and that's just the absolute value of the largest eigenvalue. So in other words, all the eigenvalues of A can be found within a circle in the complex plane that's centered at the origin, and it has this radius. So the largest eigenvalue would actually be on that circle. All of our eigenvalues would be on or within it. Okay, so now that we have the spectral radius, we can say the following, that if I have this sequence of vectors that I had before, where we obtained it by multiplying by A, then, and we're assuming that the initial vector is any non-zero vector that you choose, then we have the following, that this sequence of vectors goes to 0 as k goes to infinity if and only if the spectral radius of A is strictly less than 1. So it's not the norm that we need to be less than 1. You might think that that's sufficient, but not necessary. It's the magnitude of all the eigenvalues has to be less than 1 to achieve that guaranteed shrinkage of the sequence of vectors all the way to 0. Okay. In fact, we can say a little bit more. As a consequence of this, since our initial vector can be any non-zero vector, I can say that the limit as k goes to infinity of A to the k itself is going to be the zero matrix, and if and only if the spectral radius of A is less than 1. Okay. So this condition is going to be useful to us in our study of iterative methods for systems of linear equations, that each in the non-stationary iterative method, we find that at each iteration, the new error is the old error times a matrix. And for convergence, we need the spectral radius of that matrix to be less than 1. So that's going to come back to us then. All right. So a quick example illustrating some of the things that I've just been talking about. Okay. So here I have a 3 by 3 matrix. Okay, now this matrix is an upper triangular matrix. So in this case, getting the eigenvalues is a piece of cake. We just read them off the diagonal. So the eigenvalues so our largest one is this diagonal entry, so 4. The second largest one would be this diagonal entry, that would be 2, and then our remaining diagonal entry, the smallest eigenvalues, so that would be 1. Okay. Now, that would mean that the spectral radius of A is going to be 4. So if you take a non-zero vector and keep multiplying A by it, in fact, because all the eigenvalues are greater than or equal to 1, it's definitely not going to go to 0. In fact, in most cases, the magnitude of the vector is going to go to infinity. Also, the eigenvector, or one of the eigenvectors, is the vector E1 as the first column of identity, 1, 0, 0. And that goes with the eigenvalue 2. So if you were to actually, so you can check this yourself, A times E1 turns out to be vector 2, 0, 0, because multiplying a matrix by E1 gives you the first column of the matrix, which is this, but that's equal to 2E1, so that is the eigenvalue, and E1 is the corresponding eigenvector. Now, the other two eigenvectors for the eigenvalues 4 and 1 don't jump out at us right away. So E2 and E3, for instance, are not eigenvectors. That would only be the case if A was a diagonal matrix. Okay. So any questions about eigenvalues, spectral radius?
Your notation for spectrum. What did you say that meant again?
Oh, spectrum.
Spectrum.
Spectrum is just the set of all the eigenvalues. Yeah. In fact, I probably hardly ever refer to it, but spectral radius.
Well, it wasn't even in here, so that's why I didn't know.
Oh, okay. Yeah.
Okay.
Yeah. I guess I felt funny mentioning spectral radius about the thing. Yeah. Okay.
A to the K is just like when you make a limit, it's just the matrix multiplied by itself.
Yeah, it's just raising to a power. Yep. Actually, yeah, that's good to point out is that when you're raising a matrix to a power, you are not raising individual entries to that power. You're multiplying a matrix itself, matrix multiplication that many times. Okay. So, real pain of an operation. Okay. Now, so for sequences of vectors going to 0, you got a sufficient condition just from the norm, and a necessary sufficient condition from the spectral radius. And there actually is a relationship between the norm of a matrix, like whatever norm you're using, and the spectral radius. And we could actually use the properties of norms to see what that relationship is. Okay. All right. Okay. So let's suppose that lambda is lambda 1 of A, so the largest eigenvalue in magnitude. And let's suppose that X is the eigenvector is an eigenvector that goes with it. So AX equals lambda X. Okay. Now, that would mean that the spectral radius of A times X, the norm of X, well, spectral radius of A is the absolute value of this eigenvalue. So I'll just replace it with that. But basically, using the properties of vector norms, this is actually the second property. I can move lambda in here, so now I have lambda x. Because it's absolute value. But lambda x is the same as ax, and again by properties of norms, norm of ax is less than or equal to the norm of a times the norm of x. So if I compare this, which is now less than or equal to this, I can just cancel out the x's, the norms of x, and conclude that the spectral radius of A is less than or equal to the norm of A. And I never specified which matrix norm this is, because it can be any matrix norm. So the spectral radius is a lower bound for every single valid matrix norm you can imagine. Now, there's one case of particular interest where we have equality here. So if A is a symmetric matrix, then the spectral radius is equal to the 2 norm of A. And that'll be useful to us from time to time when we're dealing with symmetric matrices. More generally, and I mentioned this last time when talking about the matrix 2 norm, the spectral radius of A is equal to the, the 2 norm of A is equal to the square root of the spectral radius of A transpose A. So if A equals A transpose, then we get spectral radius of A squared. Well, the spectral radius of A squared is equal to the square of the spectral radius of A. So in a symmetric case, this formula just reduces to this one. Okay. All right. So to summarize what's going on here with sequences of vectors, we have some conditions on A that are all equivalent. So if one of these is true, and all of these are true. So if the spectral radius of A is less than 1, that's the same as saying that that the norm of A to the k goes to 0 as k goes to infinity. That's equivalent to saying that in A to the k, if we look at each individual ij entry, that also goes to 0 as k goes to infinity. And finally, most important for iterative methods, A to the k times any vector x goes to 0 as k goes to infinity. questions about norm, spectral radius, convergence, notation?
Yeah, so when you go to the inequality with the norms,
Yeah.
is that the Cauchy Schwarz inequality?
Oh, no.
What is
Like
that?
this right here, you mean?
Below it right there. What is that?
Oh, this property.
Yeah, from
Oh, this is the sum.
it's a product of norms or something?
It's called the submultiplicative property.
Oh, okay.
So it's worked into the definition of a matrix norm.
Okay.
It's commonly stated this way. Yeah.
When you move to what you have written under general right there,
Yeah.
which you said there's something about a symmetric matrix.
This is true if A is symmetric. This is true for any matrix.
Is that like something written down? Something like, do we have that somewhere?
Oh, page 40.
Oh, it wasn't like on a previous list or something.
Oh,
Of
I
like
mentioned
something
it.
about symmetric matrices. That's what I was talking about.
Oh,
Like, were we supposed to know that or something?
this? No.
Oh, okay. That's what I was,
Yeah. This I mentioned before.
that's what I was asking about.
Yeah. When I gave a formula for when I first introduced the matrix 2 norm, I gave this formula back then.
Oh, okay.
Yeah.
All right. That's,
Okay. You have a question? Or from down there?
If you can move it, our box is down at the bottom instead of at the top now, so if you can move it to the left a little bit,
Okay. Like this?
oh, the right, okay, the right,
Okay.
my other left.
Our face is just in the blocking corner.
Okay.
Okay, that's what I had, thank you.
I see.
Okay. Okay. Next, I'm going to use norms for a very different purpose to show something useful about the inverse of a matrix. So, suppose you have a matrix and you know its inverse, and then the matrix has changed by a certain amount. Like suppose you make a small change to a matrix, what kind of change can that cause in the inverse? And this is important because of, and this is a topic I'll be talking about either start at the end of the day or on Wednesday. Round-off error in computer arithmetic. What if if your matrix is erroneous for some reason, or if any of its entries might be contaminated by round-off error, some other form of error? How much is that going to throw off your inverse? You want to be able to say that have some bound on how much that inverse might change, because that affects how far off your solution to a system of linear equations could be. So we definitely don't want to have thrown off too much. So the properties of norms can help us figure this out. Okay, so this is about perturbations, which I'll often mention. So it's a common question in numerical linear algebra. If a problem that you're trying to solve has changed a little bit, how much does that change the answer? Okay. So I'll illustrate that with this exercise here. Okay. So again, we'll work with a general matrix norm. So a preliminary result that I'll work on is, suppose we have a matrix F, and it's known to have a norm less than 1. Okay. Now, what that would mean, because this is sufficient condition, that as k goes to infinity of f raised to the k power is going to be 0. So now, suppose I look at this matrix product. I form this matrix that is an infinite sum of, actually this is a finite sum, but then I'm taking, this is a finite sum here, but I'm letting the number of terms go to infinity. So I have an infinite sum here of powers of f. And then I multiply this by identity minus f. Now, if I were to multiply this out, then what I would get is, so starting with I equals 0, so I'm going to have I minus f plus f times I minus f plus f squared times I minus f, and so on. Then when I distribute, I get identity minus f plus f minus f squared plus f squared minus f cubed, and so on. What kind of series is this called? You can see terms, neighboring terms canceling out. What do we call that kind of series that behaves that way? Yes, it is a telescoping series. Now, normally what you do to find a sum of a telescoping series is you want to take whatever terms don't cancel. But that's not guaranteed to work because even though your terms are canceling, whatever remainder you have out here does not necessarily go to 0. But because of this right here, this condition, the norm of f being 1, this telescoping series actually does converge. So it's the limit. So what we get, after we cancel out whatever we can, we have this identity minus this term it doesn't cancel out, f to the k plus 1. And this is going to 0. So what's left is the identity. So here we have this matrix times this matrix turns out to be identity. What does that say about the two matrices in question? So what I have in the parentheses there? If A times B equals identity, what does that say about A and B? They are inverses of each other. So that means that identity minus f inverse is equal to this infinite sum of f to the I. Now, what other kind of series? We talked about telescoping series here, but this expression right here, this formula for the inverse, what other kind of series is that reminiscent of? This one, yeah. What?
Taylor expansion?
No. What? Well, more a specific kind of power series. What? Someone said it. Geometric series. So this is similar to that if you have numbers that you're adding, so sum of r to the I from I equals from 0 to infinity is 1 over 1 minus r. So you can think of this as like 1 over I minus f, which you really shouldn't do, but whatever. And this is only true provided absolute value of r is less than 1, which is similar to we need the norm of f to be less than 1 for this to be valid. So it's kind of like a matrix generalization of a formula from a sum of a geometric series. Okay. So so now we have at least an expression for the inverse of identity minus this f. So we have a way of getting the inverse of this specific kind of matrix that fits this form. However, we want to have a formula for an inverse of a more general matrix from this than this, but this can help us. Okay.
Can you scoot over a little bit that way while I'm erasing? Sorry, our little boxes.
Okay.
More. A little bit more. Alright. Thank you, that's good.
Okay. Oh, I guess I better get out of the way.
Thank you. Thanks,
Yeah.
Lauren.
And sure, we all really can't wait for that camera to get fixed.
I know.
Okay, so now, building on that intermediate result, suppose that A is a general non-singular or invertible matrix. And I'm going to let E be a perturbation of A. Now, and what I mean in this case, I'm thinking of a small perturbation of A that satisfies this condition, that this number R, which I define to be the norm of A inverse E, has to be less than 1. Right, so it has to be a small enough change to A that satisfies that condition. Okay. So what I mean by perturbation of A is we're interested in A plus E and its inverse. So what I can do is I can write A plus E. So I'm going to define my matrix capital F, which corresponds to the capital F over there. It'll be minus A inverse times E. So what I can do is I'm going to take A plus E, and I'm going to factor A out of it. So that's the same as A times identity. So if I'm factoring an A out of this, that puts an A in front of it in here. But now, by defining F to be minus A inverse E, I have A times identity minus F. Because I want the same expression as I had before. Okay. And I've already stipulated that A inverse E has to have a norm less than 1. So that means that the norm of F is less than 1. Now, because of norm of F being less than 1, that means that this matrix is invertible. Because, as I showed on the previous board, as long as norm of F is less than 1, identity minus F is invertible. It's invertible because we know what the inverse is. A is given to be invertible, so that means that A plus E, the perturbed matrix, is invertible. So to summarize, if you have a matrix that's invertible and you change the matrix by a sufficiently small amount, the changed matrix is still going to be invertible. So that's something that can be guaranteed. So it just depends on how small the change in the matrix is. Okay, but what we want to know beyond that is, can we come up with some expression for how much the inverse has changed? Okay. Because what could happen is A might only be changed by a small amount, but A inverse might be changed by a large amount. That's something that's still possible. So we want to try to come up with at least a bound for this expression here. And we can do that using properties of norms. Okay. So I have this norm, A plus E inverse minus A inverse. Okay, so what I'm going to do here is all right. I'm going to perform some factoring here to try to simplify this expression somewhat. Now, I'm going to factor out an A plus E inverse, and I'm going to factor it out to the right. So, so to help you better see what's happening, I'm going to, in the second term here, I'll multiply on the right by A plus E, and then A plus E inverse. Okay. And then what I'll do is, in both terms, I have an A plus E inverse on the right. So that I'm allowed to factor out. So now I have identity minus A inverse A plus E. Now, I'm following the notes, but in the notes I skipped a few steps, so I'm filling in those steps here. And I will freely admit it's because I don't remember what all the steps were before. So, but I figure if I tread carefully, I won't screw up. Okay, now I've factored it out. Now I'll simplify what's in here. So I have identity. So I can distribute this A inverse through this A plus E. And I'll get identity minus A inverse E. And then I have A plus E inverse. And the identities will cancel out. So in the notes, I jump from this directly to this. So that's where I'm at now at the end of that first line. Now, at this point, I can use properties of inverses, because earlier I wrote A plus E is the same as A times I minus F. So now if I take the inverse of both sides, I have A plus E inverse. Remember, the inverse of a product is a product of the inverses in reverse order. So we have identity minus F inverse A inverse. Now I can take that and fill that in here. So I get minus A inverse E, identity minus F inverse A inverse. Okay. Now, the norm of a product is is less than or equal to the product of the norms. So this is less than or equal to norm of A inverse, norm of E, norm of identity minus F, times norm of A inverse again. But now these are all norms, these are all numbers. So I can put norm squared right there. Also, from the result I proved earlier about the, oh, this is inverse, about the norm of identity minus F inverse, this is less than or equal to, oh, I skipped over that completely, I forgot to prove that. Well, that's okay, I'll do it now. So still it's in the notes, just out of order. I need to know something about the norm of this. Okay, because identity minus f inverse is the sum from 0 to infinity of f to the I. So that means that the norm, here I'm going to use the triangle inequality repeatedly, or infinitely many times. The norm of I minus f inverse is less than or equal to the sum of norm of f to the I. But the norm of f is equal to r, which is less than 1 in absolute value. So this is less than or equal to 1 over 1 minus r, where r is the norm of f. That's just using a formula from a sum of a geometric series, and this is known to be less than 1. And by the way, r can't be negative because r is a norm. Okay, so now if I just take advantage of that, I can say that this is less than or equal to norm of A inverse squared, norm of E, and then this I replace with 1, so 1 over 1 minus r, because it's less than or equal to. So actually, I'm going to write this a little differently. I want to put the E off to the side. Okay, so now, given that A is changed by this amount is how much A inverse could possibly change. And the take-home lesson here is, even if this is small, this change could possibly be large. For example, the norm of A inverse might be large. Or what if r is close to 1? Then again, this could be large. So if it's a relatively large perturbation, it could be amplified quite a bit by this 1 over 1 minus r factor. So this is one of the most difficult lessons to deal with in numerical linear algebra and actually numerical analysis in general. And that is, your problem could change by a tiny amount, your solution can change by a huge amount. There's a phenomenon known as being ill-conditioned. And that's something that we're going to learn a lot more about as we jump from one specific type of problem to another. And in some cases, we can measure how sensitive a problem is to changes, whether it's a system of linear equations or an eigenvalue problem. Okay, so any questions about the manipulations that happened here? So
R here is completely determined by the person, right?
yes, yeah.
So you can control that effect.
Well, the thing is, okay, here's an example where this comes up. Suppose the entries of your matrix come from some sort of measurement, and you have some idea of how accurate those measurements can be. You can use that to get an idea of how big the entries of E can be. Okay. So often this will happen is that we'll be able to estimate how large these changes can be in terms of the size of a change you're making in your problem. Okay. Any other questions? Okay. All right. Well, the next topic is floating point arithmetic. Okay. Since I only have 6 minutes left, all right. Let's see.
Can you shift this to the left again, please?
Over to this side?
Yes. When? Thank you.
in any numerical analysis class, you're dealing with floating point arithmetic. It's a computer that's doing the real work. Computers have limited space for storage of numbers. Typically, numbers are stored in a real number is represented using 8 bytes that holds as much information as possible about the number. It's including its magnitude and a limited number of digits of precision. And that limitation on the magnitude and also the precision can lead to significant difficulties that can come back to haunt you. So formulas that work perfectly fine in the analytical world completely fail in the numerical world. So, and I want to mention certain specific issues that are related to the homework. Okay. So the first issue is called overflow. And this is due to the limited magnitude. You cannot represent in a floating point system a number of arbitrarily large magnitude or arbitrarily small. Now, not being able to handle arbitrarily small magnitude is not a big deal, because you can just say, oh, if a number is too small, you just consider it 0, and your computation proceeds along for most part. But if you have a number that's too large, then you have a real problem, and the number is classified as infinity. So here's an example of where things can go wrong. Let's suppose that I have something like this. A formula y equals square root of 1 plus x squared. And I'm going to assume that x and y are representable. So in other words, their magnitudes are okay, but they're particularly large numbers. So what could happen is, what if x squared is too large? So x is okay, but then you square it, and now its magnitude exceeds the limit of what the floating point system can handle. And that is called overflow. And the floating point system will instead replace x by some code that can be interpreted as infinity, which actually shows up in MATLAB, for instance. So what you need to do is try to rewrite this formula in such a way that x is never actually squared. And it is possible to do that. So I gave a homework problem that's similar to this, where you have to do some rewriting. So what you can do with formula is keep in mind that y is okay, x is okay, but you just can't do this. So what can you do to a formula like this to get around the problem? Okay. The other really insidious issue is called catastrophic cancellation, or sometimes just cancellation, although in at least one instance that I know of, it was literally catastrophic. And mathematically, the problem is that if you have two numbers, x and y, that you're subtracting, and the numbers themselves are much larger. So I'm using a double greater than. This means much greater than the size of your result that you expect. So in other words, you're subtracting two large numbers that are close to one another, so close that there's a lot of cancellation going on in the leading digits, and only the smaller digits remain. Then what happens is your subtraction can be grossly inaccurate. And to give you an idea of why, let's suppose you have like 8 digits of precision. Okay, so I have a number that's represented using 8 digits, and then another number also represented using 8 digits. I go ahead and subtract them. The first 6 digits cancel out because the first six digits agree. And then I have these last disagree. I have 8 digits of precision I'm using for the numbers I'm subtracting. I only have 2 digits of precision for my answer. I've just given away 6 digits of precision. So I'm out of time, but this is a situation you want to avoid. Subtracting really large numbers that might very much agree with one another. A failure to take this into account caused the deaths of 28 American troops in the 1991 Gulf War. And since I'm out of time, I can go into that story. Some of you have heard already from another class, but I will go for the story at the beginning on Wednesday to underscore why this is such an important thing to watch out for and why it's called catastrophic cancellation. Okay, so that's all for today. I'll see you tomorrow.
Bye.
Bye. Bye, Janae.